So our next participant, Rajesh, can you hear us?
Yes, I can.
Okay, and we can hear you. So I'll.
Can I share my screen?
Yes, so let me stop this share. And then if you share screen.
Okay. Can you see my screen?
Yes. So we can see your screen and we can see.
Okay,
Yeah.
that's great. Please let me know when I can start.
I think, yeah. So our next speaker is Rajesh Kumar, and I'll just let you. I'll let you take it away from here. Thank you.
Okay, thank you very much, Dr. Jocelyn. So I'm Rajesh Kumar. I'm an assistant professor in Department of Physics, MRPD Government College, Talwara, Punjab, India. I was a postdoc in Department of Physics, Kent State University, working with. I worked with Veronica Dexheimer, and I'm very thankful to Dr. Jocelyn for giving me this opportunity to talk about my research titled Integrating Contemporary Observational Constraint into a Generalized Chiral Description of Dense Matter. I could not make it in person due to some official constraints, but I'm glad to be here. So let us start. So this is my plan of the presentation. So first of all, I will briefly discuss the introduction or motivation behind my current work, and then I will dive deep into the a particular model which I have worked in, chiral mean field model, and I will talk about the field redefinition of vector Mason fields in the chiral mean field model itself, and then at the end I will discuss results and conclude my presentation. So let us start with the introduction part. So before going deep into about my effective model and all that business, let us touch base here. So let's start with the basic quantum chromodynamics. So what is quantum chromodynamics? It describes the interaction between quarks and gluons, very simple, and the coupling between quarks and gluons in large in normal condition. What is normal condition? Normal condition is the condition where we have we are in the current state of universe, which is in the non-perturbative regime. So basically QCD exhibit two important features. One is asymptotic freedom, the other one is confinement. If we talk in terms of QCD phase diagram, which is a diagram in temperature and baryon chemical potential, so we have two major regimes here. One is the hadronic regime, the other one is the quark-gluon plasma regime. So in the hadronic regime, the non-perturbative physics we describe in terms of non-perturbative regime, and on the right side we describe in terms of perturbative regime. In the right side, the asymptotic freedom property prevails, where the coupling constant becomes very small at large energy as well as temperature. But on the left side, in the non-perturbative hadronic regime, the quarks are confined inside the hadrons, and therefore the coupling constant is very large. And what about chiral symmetry? Chiral symmetry is a very important feature of quantum chromodynamics, and it is in QCD. Chiral symmetry, QCD is approximately invariant under chiral transformation, and it is described by this transformation SU3L cross SU3R. Can also be represented in terms of vector and axial vector, and SU3 represent the three flavors of quarks UDS. So chiral symmetry is an exact symmetry when we talk about the mass of quarks when we take it to 0, but in reality the chiral symmetry is slightly broken due to the small finite quark mass. So we observe that the states with different parity have different mass in nature. For example, pi and sigma is one of the cases, and we also observe that chiral symmetry is spontaneously broken. So what about QCD phase diagram? So we previously discussed about QCD phase diagram. So in this slide, we will discuss more like the various feature of QCD phase diagram. So in the QCD phase diagram, we represent the area in temperature as well as baryon chemical potential where strong interaction prevails, and we can probe the QCD phase diagram in relativistic heavy ion collision, for example in this area, as well as with the multi-messenger observation of neutron star merger, where we can probe in this area. And many models which describe QCD has predicted a first order phase transition line with the critical point. So it states that the quark gluon plasma regime as well as the hadronic regime is well separated with a first order phase transition line which ends at a critical point, and after that critical point there is a crossover. So there is no distinct phase transition between one state to another state. So what are the various theories which can describe the QCD phase diagram, like some particular regime? So lattice QCD is the most reliable theoretical tool to study the QCD phase diagram. So it can tell us about the equation of state, strong interaction physics in high temperature as well as low baryonic chemical potential. So it solves the puzzle here. So it well describe the crossover region here, but it cannot be extrapolated to very high baryon chemical potential due to a Fermi sign problem. So here I have represented the QCD phase diagram as per the contemporary theories and experiments, like not just lattice QCD but other fundamental theories as well as the experimental observations. For example, this QCD phase diagram is in terms of temperature as a y-axis and baryonic density in the x-axis. So these regions tell us the various theories or experiment that constrain the QCD phase diagram, for example equation of state. So if we talk about theoretical side, we have lattice QCD, perturbative QCD, chiral effective field theory, which constrain the QCD phase diagram. And on the experimental side, we have heavy ion collision experiments and low energy nuclear physics results, like all the saturation properties, liquid gas phase transition, and we have observational data from neutron stars and their merger, which roughly has been shown here, which constrain the equation of state in this particular T versus NB. So these all the constraints have been encapsulated in our review article, which is been published in Living Review in Relativity in 2024, and the idea is to update this constraint every 4 years. So these are the region where we can constrain the equation of state in QCD. But what about the white region? The white region is the region where no direct theory or experiments can be applied to constrain. So we need to rely on some models, some effective models, which are based on the fundamental theories as well as experiments. So we fit our effective models on those constraints, and we try to extrapolate, we try to interpret the result in the regime where no fundamental theory can reach so far. So let us talk about one of the effective model, which is known as chiral mean field model. And so this is an effective model to study the nuclear matter. So we basically need a simplified theoretical framework that describes QCD in the desired energy range. So what we do, we interpret data and make prediction, we go back and forth. So what are the requirements for an effective model? So it should, if it has to describe a strong interaction physics, it has to encapsulate the basic properties of QCD, which is like chiral symmetry. The chiral symmetry should be restored in the particular regime, and it should also respect the broken scale invariance property of QCD, and it should have nuclear hadronic or quark matter as a degrees of freedom and their interactions. And last but not the least, it should be constrained by the first principle results, like the fundamental theories as well as the experimental or observation. So if we talk about CMF in particular, so in CMF, quarks and hadrons interactions are mediated by the exchange of scalar and vector mesons. So we have like attractive part from the scalar fields and repulsive part from the vector field, so that we have a saturated curve for nuclear force. And we have a comprehensive equation of state within the CMF, which can which treats baryon, octet, decuplet, and quarks as degrees of freedom. So CMF is a non-linear extension of the sigma model, and it is fitted to agree with low and high energy physics data, which is the constraint from lattice QCD or other experimental constraint. And for simplification, it uses mean field approximation, where the Mason fields are treated as classical field, and the pseudoscalar Mason doesn't have source, therefore they do not contribute in after this approximation. So CMF also uses a Polyakov loop inspired deconfinement potential to describe the deconfinement phase transition. So by using this Polyakov loop inspired deconfinement potential, we put quarks in our system, and we can also simulate a phase transition from hadrons to quark. So what about the Lagrangian of CMF model? It is very simple. We have a kinetic energy terms of different mesons, different baryons. Then we have interaction terms, like which for example meson baryon interaction with the coupling constant. We have scalar self interaction terms like sigma square, zeta square, and similarly we have vector meson self interaction terms. Then we have explicit symmetry breaking term, which gives non-zero mass to Nambu-Gold's to the pions, for example pseudoscalar mesons. And at last we have the deconfinement potential, which is written by this expression, and we can see it has a dependency on temperature mu b, and as a cross dependency on temperature and mu b. So these are the parameters associated with each of the terms here. Now so basically in this paper we refitted our model to the newer constraint. But if we talk about the old CMF fitting, so the old CMF fitting, which was done in 2015, it was fitted to deconfinement transition temperature, like pure gauge, from lattice to 270 MeV, and at that time it was fitted to the crossover or pseudo critical transition temperature 171 MeV, and critical point was fitted at that time 167 MeV in temperature and 354 MeV in baryon chemical potential. And it had the non-interacting mesons. The mesons were not interacting, like their effective mass doesn't change with the medium, for example pseudoscalar or vector. And then the vector meson in this case were also treated as the vector meson masses were also treated as degenerate. That means the mass of vector, all the vector mesons were the same. We realized, like, for consistent treatment of meson, we need to break the mass degeneracy of vector meson, which can help us in a better equation of state, and it can also help us describing the non-interacting mesons, and it basically paves the way for the interacting meson case. So on the right hand side I have presented another QCD phase diagram. So I have put a constraint from lattice QCD, like deconfinement transition temperature, pseudo-critical temperature, and again the critical point where there is no critical point so far, there is no sign of criticality from lattice QCD. So this is the range, and this is from the LENP, low energy nuclear physics, which is well observed. So what about the field redefinition in CMF? So what we did, we fixed the vector meson mass degeneracy using field redefinition. So we again started with the chiral mean field Lagrangian, and we only changed two terms. We improved the L vector, and as well as we improved the parameters fitting for the U phi. Why we did that? Because we wanted to update our model to the modern constraint, and we have to tweak the deconfinement potential, but tweak the parameters associated with the deconfinement potential. So first of all, we started with the field. We assumed the vector meson Lagrangian is already field redefined, and we started with the kinetic as well as the mass term, which is very simple for a vector meson. And the vector meson, the kinetic terms looks like that, which is, we assume it is field redefined. And the simplest mass term with degenerate mass, we can write it in this way. So here we can see all the vector mesons have the same mass, but we want to break the degeneracy of this mass degeneracy. We did it by using a chiral invariant term, which has a cross term between vector meson as well as the scalar mesons. So when we expanded it and we added to this Lagrangian here, so we have like the three terms now. So we have two terms before, now we added one more term to break the mass degeneracy, and we compared it with the old Mason Lagrangian, and by comparing, doing all the derivation and mathematics, we obtained few relations, and we got to know that okay, the 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 field redefined the redefined field is related to the old field with this parameter which has been written here, and it depends upon the mu parameter which was introduced in the chiral invariant term. So what we observed that now we don't have a mass degeneracy, so we have a parameter which is multiplied to this constant, okay, and for different vector Mason, the parameter is different. So after putting the values of all the constants, and we observe that we have lifted the mass degeneracy. So if we compare, so the old CMF mass, old vector Mason mass in the old CMF was 687 for omega. For everyone it was 687.33, but for the new mass it is different, which is closer to the actual value or the PDG value. So if we talk more about like vector Mason Lagrangian, we need to add self interaction terms, which is very important to get a stiffer pressure. So we started with different possible chiral invariant field redefined self interaction terms of the vector Mason.
5 minutes left.
Yeah, okay. So we started with different possible chiral invariant field redefined self interaction terms, and we started with this thing, and we have the more expanded version of it. So we have four type of field redefined couplings. So each coupling is different from the other one. For example, somewhere we have omega rho dependence, we have rho phi dependence, we have omega phi dependence, and we have linear dependence in omega and omega 3, so which contributes to the equation of state in the different level. So the field redefinition process required us to refit our model to the nuclear saturation property, the latest first principle theory, and the observational constraint. So this is the parameter table, like which parameter is associated with which Lagrangian or which potential term, and what are the parameters from different nuclear theories or lattice QCD which we have used to fix. Then we have CMF model flowchart. So we started with the Lagrangian. We have the Lagrangian. Now how to obtain physics out of it? We put it in Euler-Lagrange equation of motion. We solve the equation of motion, the non-linear coupled system, and we get something out like by fixing the model parameters using experimental constraint, and we get the multidimensional equation of state. So what about the results? So first of all, we fitted the deconfinement phase transition for the pure gauge case for different field redefined couplings at mu b is equal to 0. So we observed that like for different so C4 is the old CMF fit, and these are the new CMF fit. So we fitted it to the uncertainty band from the lattice QCD itself, like 270 MeV. The difference between CMF and the pure gauge theory, lattice QCD, is like in CMF we don't have direct gluons, but the interaction of gluons are mimicked by the exchange mesons, like mean field mesons and the phi fields. And we have fitted the crossover transition temperature, which is represented by the change in sigma and phi. So sigma basically represent the order parameter for chiral restoration, chiral symmetry restoration, and phi represent the deconfinement potential. So we, by observing the change in the order parameter, we fitted by tweaking the corresponding parameter, we fitted it to around 160 MeV, which is closer to the actual constraint from the lattice QCD itself, and previously it was fitted to 171 MeV. Then we also fitted put our critical point, we fitted our parameters in with respect to the lattice QCD results, and we got that like for old CMF it was like mu b was 354 MeV and TC was 167 MeV, but as per the modern constraint we have this region, this white region, where the critical point can be, like anywhere in this white region. So we put our critical point here, which it is not like we can just put it. It has a particular constraint, like we can change the parameter in a certain ways. So we got our critical point around 1000 MeV, but the temperature is around 130 or MeV or something. So these are the region by green, teal and pink region where the critical point cannot be there. It is excluded by these theories as well as the experiments. And we also got the critical point for liquid gas phase transition, which is around 16 MeV. So what about neutron star matter? So we also got our equation of state beta equilibrated, and we get it for also process it for charge neutrality. And we observed that if we have quarks into our system, so this is a hadronic regime, this is a quark regime, and we saw that there is a huge jump between the equation of state from hadron to quark, and we observed that it is less as compared to the previous fit. Now it is less. And we also observed equation of state is slightly stiffer than the previous fit. And when we translate it into the MR curve in the next slide, we can see we will obviously get a kink here if we have a huge jump in the equation of state, but that was now the focus of our current paper. So we presented this TOV plot, the MR plot, only for the hadronic matter. So if we add equation of state with large jump, that would show a kink, but here for the demonstration we did it for only for the hadronic matter. And we saw that like we have improved the mass radius, the maximum mass for neutron star with the new couplings. And we also observed that if we add hyperons to our system for a particular C4 coupling, the RC4 coupling, it has a slight reduction in the maximum mass. So inclusion of hyperons results in a slight reduction in maximum mass for RC4, but it still remains higher than the other coupling scheme. For example, if we compare it with this. So at last, I would just like to conclude my slide. So what we did so far, we started with CMF, and we realized like the vector meson mass is degenerate, and we fixed it by adding a chiral invariant term. And this paves the way for addition of interacting mesons within the CMF model. So right now there in this presentation I was talking, there are no interacting meson. The mass of the pseudoscalar or vector meson doesn't change with the medium, but in actuality they should do. So we used that paper calculation in some other paper, and we got the equation of state for finite temperature and finite mu b. And in this presentation, in this research work, we refitted our model using constraint from Lattice QCD, stellar observation like neutron star, as well as low energy nuclear physics. And we understood that like the redefinition of vector fields play a significant role in reproducing neutron stars with higher mass as compared to the previous fit. So at last, I would just like to acknowledge the support from NP3M as well as Muses collaborations. And thank you very much again for this opportunity to present in this conference. Thanks.
Do you have any questions? If not, I might start off. Sorry, I'm not sure where to look here. You discussed sort of an absence of constraint at the intermediate temperature that you're looking at. I guess maybe back at the beginning is where this was illustrated most clearly. But do you have any idea if observations of astrophysical events that do have some temperature affecting the dynamics of the system, so neutron star mergers or supernova or anything like that, kilonova, have you considered that kind of observation connecting with the theoretical description?
Yeah, from this QCD phase diagram, we have put this rough constraint. It comes from binary neutron star merger, like which is around, we say roughly around T is equal to 50 MeV to 100 MeV. we guess that the equation of state, whatever equation of state we get, we put that in the QCD phase diagram, and it should constrain the region there. But in the particular research, I have not taken any constraint from the BNSM, not only from the neutron stars at t is equal to 0.
Yeah, I guess like I've seen certainly folks talking about cold equation of state constraint with some of these other kilonova observations, but maybe we can discuss more if there's a connection here.
Okay,
sure.
sure.
Any other questions from the audience? Yeah.
Can you hear me?
Yes.
Okay. I have like a pretty naive question. So chiral mean field theory, what does that get us over like chiral perturbation theory? Can I work in a larger energy space now?
Sorry, chiral mean field theory and
Chiral perturbation theory, is what you said?
Can you hear me okay?
yeah, okay.
I was just curious,
Uh-huh.
what does chiral mean field theory get you over chiral perturbation theory? Like, can I now work in a larger space, or I might have missed it?
Are you asking like, okay, why would I prefer chiral mean field model over the chiral perturbation theory? Like in a way, maybe. Okay.
Yeah.
Okay, so the chiral effective field theory is based on chiral perturbation theory. So far, I know I am not the expert. So chiral mean field model is not a theory itself, but it is a model, and we observe that like if we fix it to the nuclear saturation property, we can try to explain the matter beyond the saturation density, like 2, 3 times or 4 times the nuclear saturation density. But so far, if I talk about the chiral effective field theory, it can describe matter well around 1.5 or 2 times the nuclear saturation density.
I see. Okay, thank you.
Thanks.
So let's pause here, let's thank Rajesh for his talk. Yes.
Thank you very much.
Okay, so we now have some time for coffee, and we're running a little bit late.